So this is my second time trying to do a little presentation. The first one was 20 minutes long, and I fell asleep reviewing it. So I've tried to shorten it and be a little more succinct. This is the preparation for writing a paper, hopefully to inform those who want to participate, kind of what the thinking is behind it, and maybe help to develop some hooks on how you might want to participate. This is a PDF, so I will have this Google Docs with hyperlinks to the content within it. What we're looking at is the email from the committee accepting the paper. I will provide the abstract on an email. There's a poster that was required, which is that poster there. And we'll probably work on advancing the look of that poster as this project develops. Um, so an overall, like, big picture ideas that I wanted to kind of like put out in front. Computational design is rapidly becoming a fundamental component of all design practice. That's just out of my head as a bold statement, but I think it's where my heart and thinking is. And I put a little asterisk on the fundamental, meaning that it's not everything about our design methodologies. It's a bold statement, but it's an important component of where architecture and design thinking is going today. And core to to our strategy of success, for me and my participation at Alfred, is really the introduction of these concepts at the earliest part of our program to ensure our students the greatest range of experiences for integrating this into the design process. I think that computational design, numeric design, a lot of these things fundamentally change the way we think about design, and I think it's an important element to introduce to students early. This is the theme of the conference. I'm looking for help to stay on message with the spirit of the conference to make it more useful to what will ultimately be a participation in this, hopefully. Just as a lot of us aren't familiar or very familiar with computational design, and this idea of I came up with the statement, let's say, computational design is data made meaningful. And I guess it's just a way to hold it in your head and not get mired in the details of the elements. And this kind of echoes what Zaha Hadid's statement was in times past. Math was like sketching to her when she was young. And I think that's reflected in a lot of her architecture today and the thrust of her development. And it's not to say that's the only look at computational design, but it's certainly an artistic relevant connection to it. Also, that a lot of what we're going to do and talk about may feel like folly before it becomes indispensable. I think this is part of every learning process, but there are certain absurdities about techniques and ideas that we go through. And in learning, sometimes we have to pass through that process in order to really make discoveries. I think overall, I talk about this with students and other faculty. These concepts may conflict with our school pedagogy, but even other schools. I think we have a much more hands-on the ground approach to architecture and practice, and I think that there is definitely the appearance of a conflict. But I always come back to the idea of holding back this judgment. As educators, I ask this question, obviously, do we have a responsibility to expose our students to the same methodologies and tools used by leading designers of our times? And the other, statement or thought is architecture design cannot be a mystery to our students. How these things are happening, they must be understood. It's impossible to bear judgment on what we see without even understanding how it is made. So this is just a note, really. Computational design is made more accessible via Revit and Dynamo because Revit is available in the program for free, unlike Grasshopper and Rhino, which are other parametric design programs. We really have an on-ramp to this kind of integration into our curriculum. Revit, free to all students and faculty, now host a parametric or visual programming environment called Dynamo. I also want to stress the idea that any of these concepts, while they may seem sophisticated on the face, they really can be introduced at the earliest level of the program. And one of the issues about the professionalism of the paper that was mentioned was the idea of what kind of assessment strategies we might use or think about in what we propose. This is a one of the computer viz last projects, which is a computational design. This is an example that I'm using for you right now to show you that students were able to complete this first inroads into the concepts of computational design. They make bricks or panels, and they change the length of those panels according to the relationship to an attractor point. It's all visual programming. Nothing is actually drawn in Revit, and relatively little blowback from the complexities of this. Now I wanted to quickly go through the programs that I've done, or the modules. I've tried to make the Advanced Structural Concepts class really in a modular fashion, and introduced a lot of ideas about computational design into it. And I wanted to show you that work because I think it could feed back much earlier into the program. One of the concerns I have is that we are introducing concepts that could be very useful very early in the design process, and we're introducing them late in the education. So, and another thing to keep in mind while we're looking at this is that this work is that BIM, parametricism, and computational design are all linked. And many times that's not, you think you're talking about one thing while you're talking about the other one, and that's all I can say is it's really a continuum, and it's really hard to put anything in one box as one type of style of design intervention. So I'll quickly go through the projects. One of the first projects we do is this really, I think it's an unattractive project, but I haven't revised it enough to make it both beautiful and a concise learning experience. But the idea is they make a free-form facade based on a form inside of what they design in Revit, and then they use both Dynamo and BIM adaptive component elements to create the same thing as a facade that responds to some other extraneous source. In this case, it's just an attractor point. But the goal here is to learn that you can do exactly what I said in the last statement. The continuum between BIM componentry and computational design is almost seamless and very permeable, let's say. This is a parking garage project. This is hard to really, I guess, gather the complete concept of what's going on here in the learning experience, except that you can imagine that the facade is now structurally connected back to the parking garage element, and the project here is to create an adaptive component. So the facade is now held out maybe at 4 feet or 8 feet, and by adjusting a single parameter, that facade now can be pushed in or out, and all of the components behave adaptively so that it stays as a structural element, a fully rational structural element at the same time. We kind of expand that strategy and we introduce the idea of math. We put a sine wave, we create a function that's a decaying sine wave, and we make that, we use that function to create this idea of a billowing form. So the form isn't free-formed in the concept of drawing it. It's a mathematical relationship, and even the idea that this second glass facade or curtain wall is also drawn back is done by a parametric value that is called draw. And then these are adjustable, fully adjustable, the amplitude, the amount of decay in the sine function, and the pullback of the curtains by using sliders in Dynamo. So the designer now can, on the fly, change the design to meet his aesthetic. We look at computational design to help us look at the idea of conceiving an idea and then making it something that can actually be built or fabricated. So the student creates a free-form surface, then panelizes it, applies panels to it, and then use computational geometry to identify the normal planes on the surfaces, and then lay them on a flat surface so that they could be cut out by lasers or other fabrication techniques. And even if not fabrication techniques, they're flat now and they can become technical documents. And we look at both the panelizing and the structural system under it. In this case, the structure, all of the ribbing, all of the panels are all mathematical geometry, never actually constructed. This is kind of a response to the NAB criteria for more evaluation of shear walls and other structural components within buildings. I think it's B5 or something. So I introduced the idea of a brace system. The advancement here, the parametricism, the computational design concepts are that a single BIM component is a heavy timber element, and we put attachment points. We also embed the what is the gypsum rate and fire shaft wall element all within a single BIM component, so that if walls stretch, these timber elements stretch out just as they would in any other kind of patterned curtain wall element with inside Revit. This is, I bring up a lot of these things because these are elements or lessons in that could be introduced very early. This is part of a modular construction system, but this could be introduced very early into one of the the structures course. This is a fun exploration of a facade using just a photograph or an image. This is I don't have the image in this slide, but it is a wave. And the idea is that we take data off of that wave, we determine its density, black and white image, darker areas having higher values than lighter areas, or vice versa. I'm not exactly sure how this was set up. And then we use, and this is all inside of Dynamo, we either create a surface that has a higher depth or lower depth according to that density, or we make circles. These circles in the second one could be actually laser cut screening or facade elements. And then in the last one, which is kind of a breakthrough for me personally in learning how to do computational work, we use Boolean logic to determine whether we want to have a glass element or a solid element according to the density of that random image. Now that's not to say it has to be an image. It could be sun insolation. It could be any other kind of criteria that we would want to map to that surface and then control its appearance or function. Glass structural element. This is tornado, commonly very typical new architectural element that's being introduced. We use computational geometry to pattern that and create elements. This is the idea here is we take that wave facade that we worked on and we look back at reducing it to or putting structural components behind it. So we generate all of the trusses that you see here are generated inside of Dynamo based on addition and subtractions of existing geometry and then sweeping tubular or rectangular components along those. So all of these ribs or all of the structural elements are created right inside of Dynamo, and we can select whether we want to have 4 trusses or 5 trusses or 6 trusses, how deep we want those trusses to be, all within parametric sliders. This is a fun a project of looking at Calatrava's concepts of skeleton type structures. We use an adaptive component. In this case, it could be made out of wood. This could be part of a structures unit. We look at then applying that to forms that are generated in Dynamo and defined by sweeps and curves, and those have sliders. They're indicated up here. And we can change all kinds of values about this. And this actually makes now the idea of modifying this design accessible not only to the architect but other collaborators on projects. So I think this is an exciting aspect of what computational design can do for opening up design process. This is T-splines. This is the idea here in looking at computational geometry. T-splines are a mathematical 3-dimensional concept similar to B-splines, but really in 3 dimensions. And they allow us to create different radius and thicknesses to what are just wireframe shapes, and quickly creating interesting geometry. And in this case, we not only create geometry for the buildings, but we can flatten it out and look at the idea of using subtractive systems within inside of the computational environment to create mold systems, what might be used for building components later on. And finally, this is a tower. I think it's the requirement of all computational designers or designers in general to look at the idea of exploring form, especially in tower forms. In this case, there's no design work done in Revit. These are all, you make a floor plate, you mirror it, you twist it, you raise it up through space, you add glass, all computationally. But I think it's a fun experience in learning these techniques. And I think that students quickly learn that when they see the geometry of the towers that are currently being constructed, they have a fundamental idea about the basis of a lot of the thinking. So from now on in this presentation, these are background papers, things that if you have interest in certain elements of teaching, you might find relationships here. They all have, most of them I think have hyperlinks. There's some YouTube videos. This is, I think, a really important piece to look at. This was in ArcDaily, but it's basically how computational design will change the way architects work, which means how we teach architects. So I think this is an important one to take a peek at. A lot of people are doing all kinds of fun, neat experiences with Dynamo. So there's and computational design. And so I have some links here. This is probably the highest level of work that's happening with computational design. What's really neat about it is how accessible some of this information is. You'd probably be relatively intimidated to look at this video without any ideas about these design concepts of computational design. But amazing amount of work is available, and actually quite easy to reduce down to teaching elements. And this is a BIM designer at Zaha Hadid's Architects, and they really go into some look at some really advanced projects. This is some background papers, especially pointing the direction that there are other people, a lot of other people looking at how to integrate this into design. I think this paper, one of the proposals of this paper, and I think that's, I'm just fast forwarding through these because I don't think they necessarily warrant any kind of extra discussion. Here's one on space planning. So anyone with an interest in interior design, there is quite a bit of work with generative design coming up with alternate plans and artificial intelligence and other ideas about advancing the design of interiors. And here is actually really quite a simple thing. It's a little bit, looks like a little bit of complicated code, but it's actually applying colors to areas in buildings to help people better understand functionality. Space planning arrangements, affinity, space affinities, connections, all of that, all part of an exciting part of where computational design is going. Here is Autodesk with an automated generative design responding to, this is a look at, I believe this is their offices. This is a video, a YouTube video, so I don't know exactly what the source is. And then there's an interesting article about just the idea of buildings in general getting more complex and how we need to be able to deal with that. So the closing action item, I hope you'll see that there are a lot of exciting opportunities for this. I'm sure there's a lot of intimidation about the concepts, and one of the goals of this paper and actually the program is really to increase comfort level and the ability of all faculty to understand these concepts and embrace them well enough to feel comfortable with their integration into curriculum. So I'm looking for some help with the paper. I need to know if somebody wants to participate by December 8th. I'm going to submit a full paper on my own if I don't, and I've had 3 people express interest, so I think it's a great, and we'll have multiple authors on this. I need help in, besides just people to feedback on, participation in the more professionalism of my writing, and the issues of citing references and any other help that experienced faculty might be able to experience, and in an experience I wasn't trying to exclude anyone, can help me with. So I appreciate it, and I appreciate your time to review this.